Hello and welcome to this second lecture on the subject HVDC transmission and facts. In the last class, we have seen the introduction to the subject, the course outcomes, and the basic power flow problem. Today, we are going to compare the options which can be used for large scale transmission of the electrical power. Here we are going to compare two technologies, that is the HVDC and AC transmission. When I am saying AC, it is understood that I am talking about the high voltage AC. So traditionally we have been using high voltage AC transmissions for transmitting power over large distances, and now we are also focusing on HVDC. So how they compare with each other, that is what we are going to see in this class. So there are 3 points on which we are going to compare the HVDC transmission and AC transmission. These 3 points are the economics of transmission, technical performance, and reliability. How these two technologies fare on these 3 aspects is what we are going to discuss. And then we can use, or we can decide that which particular transmission system should be used for a particular set of application. Moving on, let's see the first comparison point, that is the economics of transmission. Now, when we talk about economics, we have to talk about the total cost which is incurred on transmitting power from one point to another point. So this total cost can be divided into 2 parts. First is the investment and the second is the cost, or we can also say the capital cost and the running cost, right? So what are the parameters that we need to understand or we need to consider when we talk about the investment? So when I say investment or the capital cost, these things are involved. The right of way. So when you take any transmission line from one point to another point, we don't have a highway which is available for us freely to take the transmission line. We have to talk to private parties, to governments, and to different agencies as well in order to acquire the right of way. And this right of way will of course come at a certain cost. This can be a one-time cost, or this can be a recurring cost on a long-term lease as well. Then there will be an investment required for the transmission towers, for actually constructing the transmission towers. There will be an investment required for the conductors, the insulators, and the terminal equipment. So all these things form the investment or the capital cost of any transmission system, may it be the HVDC line or the AC line. And then there are operational costs. So here there could be many operational costs. For electrical engineering purpose, we restrict ourselves to electrical losses, because electrical losses form the major part of the operational cost. So we will consider both the lines, the HVDC line and the AC line, on these 2 aspects of the fixed investment or the capital investment and the operational cost. So let's first see the investment comparison. So as you can see on the slide, a DC line with 2 conductors carries similar power as an AC line with 3 conductors of same size at same insulation level. Okay, so what do you mean by same insulation level? Same insulation level means if you want to insulate 500 kilovolts or 800 kilovolts, okay, and if you want to transmit, let's say 2000 megawatt capacity, okay, so 2000 megawatt, if you want to transmit from point A to point B, the DC line will require only 2 conductors, whereas the AC line will require 1 extra conductor. Okay, so you can see the comparison here. Now plus minus 500 kV DC, okay, the root width is only 50 meters, whereas to carry the same amount of power, okay, which is around 2000 megawatt, to carry the same amount of power, you require a 800 kilovolt AC line with the root width of 85 meters. Now when I say the root width is 50 meter, that means the right of way that I will need is much lesser as compared to the right of way I will need here, because 35 meter distance is anyway there, and we are saying that the insulation levels are same. So you can transmit 2000 megawatt of power in these three options. Either you can use a plus minus 500 kV DC line, or you can use a 800 kV AC line, or you can use two 500 kV into two lines of 500 kV AC each. That will require 100 meter of distance. So you can see the fixed cost of if we compare the fixed cost, then the DC line fares well, because it is using one less conductor and it is also using the distance, or the root width is smaller as compared to the AC line, right? So this is one point of comparison as far as the investment is concerned. Now let's see the second part. So the first part was related to the capital cost, because when you say that you require one conductor less, that means less number of towers, less number of conductors, less number of insulators, everything will be reduced in that proportion, and hence the cost can be less. Electrical loss. Now HVDC has less power loss as only two conductors and less resistance, 67% loss as compared to AC. Why? Because there is no skin effect. Because there are only two conductors, so the I square R loss will be anyway less, okay, and the loss is 67% of that of AC. So if there is a 100 watt loss in AC system, here you will have 67 watt loss. So there is a good saving that you get here. There is no skin effect. What is skin effect? So in AC systems, the cross sectional area of the conductor artificially increases because the current tends to flow on the outer periphery, and it is not flowing through the entire cross section area, right? So the cross sectional area of a round conductor available for conducting DC current is the entire cross sectional area that is available. For AC current, you have the less number of cross sectional area, and if you use high frequency current, even more cross sectional area is gone. So the AC resistance increases as compared to the DC resistance, right? So in DC systems you have no skin effect, so that's why the losses are less. One conductor is less, that's why the losses are less, and there is a less significant corona effect. Now I'm not talking about the COVID-19 guys. You know this corona is a high voltage phenomena, and this effect is also pretty less in the HVDC system. The significance is very less, so losses are less. In HVDC, we don't need any reactive power compensation. Now what is this reactive power compensation? So whenever you are using an AC system, if it is drawing inductive current, to balance that we need to provide a capacitor bank. Okay, so this capacitor bank requirement is not there on the transmission line. Please mark my words, on the transmission line. Okay, however, there is a big negative in terms of HVDC which overpowers all the positives, and that is the terminal equipment cost is higher in HVDC due to converters and filters, right? This is one of the major reasons why HVDC was not so prevalent earlier. The terminal equipment means the converter and the inverter, or the rectifier and the inverter. So there are two converters at two places, sending end and receiving end, and these two converters use power electronics, and the cost of this power electronics is way too high as compared to AC systems, because AC systems simply require a transformer. They don't require any kind of a conversion and inversion. So the cost of this terminal equipment is much higher, and it also requires a lot of filtering. So this particular cost offsets the advantages which HVDC is giving you in terms of the rights of the way, and in terms of the conductor, reduction of the conductor, in terms of skin effect and all, right? But there can be a possibility that after a particular distance HVDC may be, okay, so let's see that what that distance is. That distance is called as the break-even distance. So now we are now focus on this graph which is shown here. Okay, on y-axis we have cost and on x-axis we have the transmission distance. Now as you increase the transmission distance, the cost of the AC system will keep on increasing, and the same will happen to DC system as well, because when you are increasing the distance, the number of conductor length required will be more, number of transmission towers will be more, rights of way cost will increase, and everything will increase. So this red line is indicating, this particular red line is indicating the increase in the cost of the AC. The capital cost AC substation is much less. You see, this is the capital cost. On y-axis we have the cost. So the capital cost of the AC substation is much less as compared to the DC substation. However, as the length increases, the AC cost, the overall cost of the AC system keeps on increasing. Okay. If I, on the other hand, if I see the DC system, then in the DC system, the capital cost is much higher. It starts way too high above the AC system here. But the rate of increase is low because the rights of way are less, the losses are less. Okay, so there is a distance, the transmission distance, above which DC system performs better, it costs less as compared to the AC system. Okay, this distance is called as the break-even distance. This distance is called as the break-even distance. Okay, so what is this distance? So it is approximately 500 kilometer for overhead lines. So earlier, if you read the old books, this distance was given as 800 kilometers. But if you see the new books, if you compare the today's technology, then if you want to transmit power above 500 kilometers, and if the power transmission is good enough, then the HVDC line is more economical as compared to the AC line. And this distance is much smaller when we compare the underground cables, because in AC systems the underground cable will require a lot of reactive power. Okay, so this distance is only 50 kilometers. So if you want to transmit power just above 50 kilometers underground, then you should go for HVDC system, right? So here we have assumed that the right of way cost are same for AC and DC, and that will be always true, because the person who is having the land will not ask you which line is going, whether it is AC line or DC line. Accordingly the cost will be, no, it won't be different. Okay, so the break-even distance, remember, this is the takeaway from today's class. The breakaway distance for the HVDC is 500 kilometers or 300 miles roughly. That means if you go beyond the distance of, if you want to transmit a power beyond a distance of 500 kilometer, you can seriously give a thought for the HVDC line. Of course, the power should be good enough. The amount of power should be good enough to transmit. You cannot say that I am going to transmit only 10 megawatt. That will be a joke. So if you are transmitting good enough power, then 500 kilometer and above, you should consider HVDC. It will be a more economical option. I am just talking about economics right now. Okay, we'll see the technical things and other later on, but right now I am only focusing on economics. So as far as economics is concerned, money is concerned, there are two costs, as I told you, the fixed cost and the variable cost. In the fixed cost, HVDC line fares better because it requires one less conductor, it requires less right of way. In the variable cost also, the HVDC fares better because it has less losses, less electrical losses, it has no skin effect and less significant corona effect. Because of this, the running losses are also less in HVDC. Only problem with HVDC is its terminal cost, terminal equipment cost, which is very high. And this also can be offset if you go beyond a distance of 500 kilometers. So remember this, if you are going beyond 500 kilometers overhead, go for HVDC. If you are going above 50 kilometers underground, go for HVDC. Alright, so I guess that you have understood this, students, the economics comparison of the economics of transmission of both the systems, HVDC and AC. Right? In the next class, the second point, okay, that is the technical performance. Thank you for watching the video. Thank you so much.